In the previous lecture, we had seen that solutions to systems like Ax equal to y, uh, in some cases when there are infinite solutions, they can be broken into two pieces and we can write them as Ax particular solution and plus a vector from the null space, and that would be equal to y. And in this case, it will be clear that that particular solution will be equal to y, and then you will have the freedom to choose the null vector in whichever way you want. Any kind of a linear combination of null space vectors will give you, can be added to this particular vector, which is a particular solution, therefore. And when you add, you will get another solution to this system of equations. Now, how to find this particular solution? Because if the null space is non-empty, if there is more than zero vector in the null space, then the matrix A is going to be singular. Then how do you talk about inverse? You cannot say X is equal to A inverse Y. So we will just look at a way to go around it and find that particular solution. So let's say we can, by performing some similarity transformation, we can reduce a system of linear equations. Let's say we start with Ax equal to Y, and then we perform these similarity transformation and then change the basis for this vector representation. From Sx we'll get x prime, and from Sy let's say it's y prime, and we are using that's why we're calling it a similarity transformation. We are using the same space for the solution space as well as for the right hand side of the equation. So now we'll get a similar matrix A tilde, right? And that times x prime is going to be equal to y prime. Now we have to find the solution to this system. Now we have reduced. Now let's say if this A tilde, for now, let's say A tilde is a diagonal matrix. Now only a certain kind of matrices can be converted into a diagonal matrix by this similarity transformation. Those such matrices are called diagonalizable matrices, and they satisfy. We'll actually learn more about them when we talk about eigenvectors, eigenvalues, and then from there we will go to the diagonalizability condition also. For now, it's sort of, you can think of it like is a convenient way of showing this. It is not a requirement for this procedure, but it's a big assumption, of course, at this stage. But it is not a required condition. We'll just see how to go sort of about these problems. So let's say we could reduce into a diagonal form, and then the system would look like lambda 1, lambda 2 times x1 prime, x2 prime is equal to y1 prime, y2 prime, and so on. And as we had seen earlier, if we can reduce it to a diagonal form like this, then the solutions would be readily available like this, right? The system, you would have solved the system of equations. Now, of course, the trouble is that if it is an invertible matrix, then you will have all the diagonal entries that you have here would be non-zero. Then you have a unique solution like this in this form. But what if some of these terms are zero? So some of these terms can be zero. In that case, how would you sort of solve this system? In that case, what will happen is, if it's a consistent system, then you would see that the right hand side would also have zeros corresponding to those diagonal entries, the rows which will have diagonal entries, that means which will be completely zero essentially, right? Like this. So those equations would reduce to zero by default, right? So so this system of these remaining equations we can completely ignore, and essentially that means that this part of the equation where you have 0 xk equal to yk is equal to 0. Of course it has to be, because otherwise it will not be consistent. So if it turns out that one of these yks belonging to these equations, set of equations, if it is non-zero, then you will say there is no solution. Of course, this is an inconsistent system. That's what it would mean. But if the corresponding yks are 0, then you have infinite systems, and which just means that the remaining xk values, you can just choose any value for them, and it will be perfectly okay. That's what it means, right? And the non-zero, I should write it here, that these non-zero values, non-zero lambda 1 to lambda n, define the nature of the, if I can add here, particular solution. They define the nature of the solution or the nature of the particular solution that you have, right? So now if we, so what we have realized is that we have received sort of got some sort of a particular hint of a particular solution in terms of these non-zero diagonal entries that you have here. Okay, so at this stage, what we can do is we can reduce this system instead of worrying about, let's say, if we write it in the block diagonal way as shown here. So this system here has been denoted by this system here. So this is another small diagonal matrix. Diagonal matrices are normally represented as lambda. Here it's a capital lambda m cross m. And you have a vector with non-zero values xm corresponding to the non-zero values xm prime x prime m cross 1, and the remaining n minus m entries can be randomly chosen. You can choose them whichever way you want. And this on the right hand side, the lower portion below m values, m rows, all have to be 0 for consistency. That's a requirement. So now we can sort of remove the unnecessary part from here, and you would reduce the system as lambda m cross m x m prime as m cross m is equal to y prime, right? So now from here you can immediately write that these values x prime m cross 1 should be equal to this. That's also pretty clear. Now we want to place it back into that original system of equations. Now we know that x prime vector, keeping these as 0 vectors, because let's say we have chosen them as 0, doesn't matter, because they could have been chosen anything, so we'll just keep them as 0. And then this particular solution is essentially, if you want to go back to the same basis that you were using earlier for the actual set of variables, which will be s times xp. Okay, so this x prime m cross 1 and this set of 0 and m minus m cross 1 values is equal to s times xp. S is an invertible matrix, of course, because it's used for change of basis. This is equal, this is the left hand side, and the right hand side, same way, ym cross 1, the same matrix S, you can write as S of y. Now you get this. Now you can take this S to the right hand side. From there, you'll get X as S inverse this diagonal matrix which has been inverted into SY. Okay. Now this, if you look at this matrix that you have obtained, S inverse lambda, if we can call it, into S, this matrix, let's say, is A prime, the inverse. Okay. Now, what we have done is we have done some sort of a, it's not exactly, it's the inverse of that matrix, but it's sort of some inverse of that matrix. And this kind of a this kind of inverse is called a pseudo inverse, and it's used extensively for non-square systems also. When we are talking about least square method and all, we can sort of, we use this concept of pseudo inverse. This was introduced by Moore Penrose. It's called Moore in Penrose inverse also, or pseudo inverse as it's generally called. This is pseudo inverse of a singular matrix. So you can sort of cannot invert a singular matrix, but you can always get an approximation for the pseudo sort of inverse. And that is just to obtain the particular solution. What we have done here is we have completely neglected the null space part, where that part we have ignored, and then we have obtained some sort of a inversion. So when we talk about mappings with the kernel space, we say that the remaining vectors have a one-to-one correspondence, and these are getting mapped to 0. right? So those set of matrices, those part which are getting mapped directly to the range of uh, this mapping, they can be sort of taken back, like, right? You can obtain the inverse. So if you know this, you can roughly say it must be coming from here, correct? Of course, there will be a set of vectors which will be formed by a linear combination, like from here, which is this particular vector is essentially, let's say, this is, let's say, xp, this is, let's say, xn. So let's say this vector is xp vector and this vector is xn vector. Now you can make a linear combination. So that would be like u plus w we were doing earlier, like two subspaces we were adding. Here we are adding two subspaces again. Then you'll get this vector. This vector is essentially xp vector plus xn vector. Now this vector will also get mapped to, let's say, will be mapped to this one. So there will be tons of such vectors also. So right now what we have done is we have taken away all these set of vectors. We have just kept those vectors which will be mappings only to one map vector here, right? We can think of it as a range of A transpose also. So these, if we remove these set of vectors which are obtained by linear combination of P and xp and xn, then you are left with this part of the domain which is getting mapped to only one vector. And then it's easy to say that there is an inverse. That's the inverse that we talk about in this case of pseudo inverse. That's the inverse that we talk about. Okay. So this is the way one can obtain a particular solution. Okay, now we'll move to the next topic, invariance of a matrix. Of course, I could have waited for the spectral method the spectral decomposition to be introduced before this, but we can already talk about some invariance. And now that we have talked about the diagonal version of the matrix to which it is similar. So let's say by performing similarity transformation, we can, if we can reduce it to bare minimum, it could be a diagonal matrix. If it is not going to be a diagonal matrix, it would be something which would be close to a diagonal matrix, which is called the Jordan form. We'll talk about it later when we talk about spectral decomposition. For now, we can, at least by performing similarity transformation, we can reduce to near diagonal matrices. Any matrix can be reduced to a near diagonal matrix. So having said that, so there are, when you're performing such operations, clearly, and there are certain properties which you have to maintain. That's why you say that the nature of the solution is not changing, because you're maintaining certain properties of the mapping. And therefore you say that the nature of the solution is not changing. It is determined by certain properties which remain invariant under these transformations, or transformation of bases, as you can think. So, so as we have talked, when we are talking about the pseudo inverse, so we saw that we can reduce a matrix if we can reduce. If we can reduce into a diagonal matrix, we could see that we can talk about finally the solution that you will get would be because of the final diagonal entries that you're left with. Okay. So the diagonal entries that you get once you have diagonalized the matrix, those diagonal entries play an important role in finding the solution or defining the nature of the solution, right? And as I said, if it is not diagonal version, it would be near diagonal, and as we will see later, the diagonal entries would still determine the nature of the solution. It might not be diagonalizable completely, but once you have reduced it to bare minimum form, as close as possible to diagonal form, we can talk about the diagonal entries defining the nature of the solution. Now, of course, these diagonal entries, they depend on in which order you have performed these row reduce operations and the corresponding column operations. So what that means is that when we are trying to reduce your similarity transformation, when you try to reduce a non-diagonal matrix into a diagonal matrix, so what you do is you perform some operations on the row and reduce whatever is below to 0. Okay, then you can perform the corresponding some column operations in this direction, and then you can reduce whatever is non-zero to 0 in this way. So in row, when you do row operations, the target is to reduce zeros in this way. And when you're talking about column operations, you are essentially moving left to right and trying to reduce it to 0. So if you're using the same kind of scalings and all the same operations that you use to do perform to make it 0 here, if you use the same operations on this side also, so you perform one operation like this, then you perform another operation like this. If you perform these operations in column, in a row way here, and in the column way in this fashion, in that case, uh, for a given matrix, you can show that you will get, you will reduce it into a diagonal matrix, and this matrix would be inverse of this matrix. That's what it reduced to. It should reduce to. Okay. So now, having said that, suppose so when you are doing these operations, you are sort of choosing a certain different people will go about it differently. So of course, the final form of these diagonal entries may be different. So somebody may obtain by these operations as lambda 1, lambda 2, lambda 3, and so on. And somebody else doing similar operations in a different way may end up getting lambda 2, lambda 3, lambda 1. So you can see that they are both similar matrices, but then they have been when you perform these operations, essentially the arrangement is non-unique. So they are unique in some ways, but they're non-unique to the extent of permutations of the arrangement of the diagonal entries, right? So the exact order may not be what you will get. It can be different. Now, having said that, so you'll have you will get, you can just list them down in any order, lambda 1 to lambda n. They are the diagonal entries, let's say. Okay. Of course, some of them could be 0, some of them may not be 0, but these are the diagonal entries. So if the order is not important, then there are certain other properties which will be important. Let's say because these entries are same, order is not same. But if you add them, then it doesn't matter which order you add them. So essentially, you can say the summation of these diagonal entries would remain unchanged during this process. Okay, so between all the permutations, it will remain the same. So finally, you're saying these are the values which determine the nature of the solution, nature of the exact mapping that you're using doing through A. So you can say that the summation of these diagonal entries will not change. Okay, and this summation essentially is nothing but the trace of A. So this summation is not changing. Then I can also add square, and I can do lambda 1 square, lambda 2 square, and so on. That will also remain unchanged, right? I can take a complete product of them. Then it doesn't matter if I'm doing lambda 2 into lambda 1 or lambda 1 into lambda 2, it doesn't matter. So this product will also remain unchanged, right? So it will turn out that the summation of lambda I will remain, we can sort of something like trace of A. It will turn out that it's nothing but it's the same as trace of A. And the product of these entries or diagonal entries would be determinant of A, right? So, so these are the invariants. They don't, these uh, the trace of A, determinant of A, they do not change under change of basis, or in other words, under change by when you're performing similarity transformations. So suppose if you're mapping V to U and you have defined that there's a mapping which is A, which is taking V to U, in that case, you expect that you can take a vector V and represent it using any basis, right? So it will get mapped to U only. And if you're talking about V to V mapping, then the change of basis is equally applied. So let's say you're talking about mapping V to V, then the change of basis that you have done used for V and change of basis that you've used for U, it doesn't matter. So if you're using the same basis for this to this, for both these, for the vector space, then this V to V mapping or V to some other vector mapping that has been achieved using the matrix A will not depend on what basis you choose. And that's what is meant by S inverse S A X is equal to Y, because that's essentially saying ASX is equal to SY. So it doesn't matter how you choose this, how you represent this vector, it will get mapped. The mapping nature of mapping will not change, right? This is what the meaning of similarity transformation is. And under such a transformation, all your these properties should remain same. Some basic properties of the mapping should remain same, which are defined by these diagonal entries. So you say trace of A remains unchanged, determinant of A remains unchanged. There are a whole lot of some other numbers which can be obtained. So for example, lambda 1 square, lambda 2 square is unchanged. Lambda 1 cube plus lambda 2 cube plus so on also remains unchanged, because under these operations, when you're taking these n values, you're arranging them in an order where the order uh, of these arrangements do not matter. So these, like summation order doesn't matter, summation of squares order doesn't matter, summation of cubes order doesn't matter, product of these things order doesn't matter, or having these kind of products, lambda 1 into lambda 2, lambda 1 into lambda 3, and so on, plus all combinations if you take into account, then the order will again not matter, right? So if you take into account all these arrangements, it will not matter, right? The order will not matter, and all these quantities that will obtain this way will be invariants of the matrix or the mapping. We will discuss more, as I said, about these variants when we talk about spectral decomposition. When we talk about eigenvalues, eigenvectors, this becomes really important to understand this. Okay, and these numbers will come out by themselves when we try to analyze the eigenvalues or eigenvectors. For now, we'll just look at trace of A, some properties of trace of A, determinant of A. These are two most important invariants that normally you will get to hear. So what is trace of A? Trace of A is essentially summation of all the diagonal entries. Okay. So now that means trace of A is going to be A11 plus A2, and this is summation. You can write it in this form: AII summation I running from 1 to N. Now suppose if we talk about trace of A into B, you can write A into B as AIJ BJK. That's how you multiply summation over J running from 1 to N. Let's look at this thing to get, this is what you gives you the product, which is CIK now. So essentially, let's just look at 2 cross 2 matrices just to show this. Okay, you can do it for a general matrix also eventually, but just to show this, I'll just use 2 cross 2 matrices, and this product will be given by, you take this multiplied by this. Okay, this gives you A11 into B11. Then you say plus this into this. I'm sure most of you have done it already. I'm just repeating it here. And similarly, you can obtain the next element as A11 into B12 plus A12 into B22, and so on. You get the 4 elements. Okay, and these elements essentially, if you want to break it down further, if you want to look at, let's say, the element from here, if you just see CIK, suppose, let's say we choose this. Now here you are talking about a system where you have here C11, C12, C21. This is the resultant matrix C. Now you can write C11 as, you can see, A1J, and then you say BJ1, and summation over J running from 1 to 2. That's what C11 is. Correct? Similarly, you can talk about C12. So C12 is going to be summation j equal to 1 to 2 a A1j bj2. So you can check j is 1, you get A11 and B12. J is 2, you have to add to it, you say A12 B22 and so on. That's how you get it. Okay, so now clearly you can also think of them as the way you will obtain them normally, how this multiplication was defined in the first place, how you define this. The reason for this way of multiplying two matrices comes from the mapping. So let's say A11, A12, A21, A22 is there, and then you have another mapping B11, B12, B21, B22. Now objective is to replace this entire mapping, which is mapping. These are of course two mappings. So you have a mapping V to B to V. In this case, V is R2, and you're mapping it to using first you're using B mapping and then using A mapping. And now you want to say that you want to get the entire mapping as one shot you want to do using some C matrix. Okay, so that's what the objective is. So what you do is this way you will say x1, x2 is there. Okay, this is the vector which you're mapping. Let's say this x vector is here. Okay, so you do the B mapping first. When you do the B mapping, you will have this is the A mapping which you'll do later, and here you'll get B11 x1 plus B12 x2 and B21 x1 plus B22 x2. Okay, after this we do the A mapping. Now when we do the A mapping, we'll write this as A11 into the entire B11 x1 plus B12 x2. Okay, and then plus you have A12, this one, multiplying this one. So A12 into B21 x1 plus B22 x2. That's one something. Then again, the lower row, again, you can do the same thing. B21 into B11 x1 plus B12 x2 plus A21 into B21 x1 plus A22 into B22. Oh no, the entire thing actually. So A22 into the entire thing. So you'll get B22 into x2 like this. So you get this resultant vector. Now, of course, you want to split it again into x1, x2. So you'll get this as A11, B11 plus A12, B21 into x1 and plus you have A11, B12 plus B plus A12 into B22 into x2. The lower one you can write the same way, A21 B11 plus A21 B21 x1 plus A21 B12 x2, I'll just write the x2 later, plus A21 into B22 A2, this should be A22, sorry, this should be A22, so A22 A22 into B22 x2. Now we take the task of separating them again into one vector and thing, a matrix. So we get B1, A12, B21, A11, B12 plus A12, B22, so on into x1, x2. Now this is what we call as C now. So you'll get C times x1, x2, right? And so now you can compare the terms that you get like this. You'll get your definition of multiplication of matrices from here, the way we have learned to do in our earlier classes. So that's why you multiply like that. Anyway, so coming back to the properties of trace, you will write trace of AB as so first you take the product. So this is Aij Bjk, and then you have to write the K also as I. So it will become summation of all the terms Aij into Bji. You can rearrange it in a different way by keeping B here and A here. So that way you write Bji into Aij, because this order of summation doesn't matter. So now you can say that this is essentially a product of B into A and not A into B. So you'll get this is same as saying trace of BA. So trace of AB using this kind of initial notations we have shown is same as trace of BA. That's the first property. In the same way, if you have three matrices, you're multiplying A, B, C, you will write this as any element of A, B, C. If you want to write some element, let's say in this case, we are writing it as I into L, let's say. It will be written as A, I, J, B, J, K, C, K, L. This is summation over two quantities now, j running from 1 to n and k running from 1 to n, let's say. So then the trace would be trace of ABC is essentially summation of ABC I running from 1 to n. Now we replace this L with I and then put it in the summation. So it will be I equal to 1 to n, summation k equal to 1 to n, and summation j equal to 1 to n. Aij, Bjk, Cky. That's the product. Now, the same way that we had arranged it here in the case of a product of two matrices, in the same way, we can do the rearrangement here. You can see that already happening. So we can say Bjk and Cki looks like a product. And then I can push back A. So I can write this as Bjk into K should match and I should match for the product to be correct. And so now I can convert it into something like here it will be, this is essentially B's into C into A. And this the entire thing is trace of B into C into A. So trace of ABC is trace of BCA. And using the same combination, you can say, if I rotate it once more, so I send B at the back, C at the front, A will come in the middle, you'll get trace of CAB. Now, if I do an odd sort of a kind of a permutation, if I sort of say not odd kind of permutation, some different permutation, if I take, for example, CBA, if I'm just doing kind of rearranging this part without taking care of the order, then it will become CBA. But then trace is not going to be equal. So trace of CAB is same as trace of BCA, same as trace of ABC, which is not equal to trace of CBA. That you have to keep in mind. Moving forward to determinants now. So for determinants, you can say that we'll sort of look at more carefully. The notation that we'll use is determinant det of A as the function for determinant. Many places you can write the determinant by using these two vertical bars like this. This is also another notation for determinant of A. Now, how to evaluate determinant? So this you have learned it in sort of, I'm sure most of you already know this. I'll just quickly go through it once. So if it's a 2 cross 2 matrix, then what you do is you take A11 multiplied by A22, that's here, and then you take minus of A12 into A21. That's the determinant of a 2 cross 2 matrix, correct? Now for a 3 cross 3 matrix, you have to do slightly more cumbersome, and calculating determinants is mostly an expensive affair and should be avoided in numerical calculations as much as possible. Right, but what one can do a lot of other things without having to do compute determinants, but let's see uh, how to calculate 3 cross 3 matrices determinant. So in this case, we'll choose a row. Let's say we choose the top row, A11, A12 is the top row that we choose. Then this is called the submatrix. Let's say this is submatrix corresponding to the element A11. Get the minor matrix corresponding to this. So what you do is you say A11 into determinant of the smaller matrix, submatrix that you have. Okay. That will give you, and that you know all 2 cross 2 matrix, you know how to evaluate the determinant already, right? Then you pick the next element, which is you have to take as minus A12. You get the minus here, minus A12. Then you'll get these A21, A31, and A23. This is going to form, these 4 elements are going to form your submatrix. Take the determinant of that. So it will be determinant of A21, A31, A23, A33. Then you say that take the last one, A13, and this is going to be your submatrix. And you take the determinant of that. That's how you calculate determinants. And if it's more than 3 orders, then you can follow the same, exactly same procedure. Only thing is that in the first step, you'll get uh, for a 4 cross 4 matrix, you will have this element A11, and this submatrix will be a 3 cross 3 matrix. And for that determinant of that, you can use the same procedure here. Like in this case, we used the same procedure for evaluating this determinant of submatrices, right? Anyway, we call these, we denote these submatrices by some minor M11. M stands for minor, minor 11. 11 for the corresponding element 11. Okay. So this minor essentially is, this matrix essentially is leaving the one row corresponding to the first element 1 and corresponding to the second, this is column. So leaving the first row corresponding to the first letter 1 and the second number 1 for the column. So you remove this column and this row, you get another square matrix, which is submatrix, which is what you're calling as 1 1 in this case, because it's corresponding to A11. Same way, A12 would be you will call this one as M12 and this one as M13. So 13, M13, and you can calculate the determinants of these. So these determinants you know already how to calculate. This is for the 2 cross 2 matrices. This way you can calculate the determinant of a 3 cross 3 matrix. So suppose if you repeat one of the rows. So if you say by mistake, if you start saying that you are writing A12 into determinant of M11 minus A22 into determinant of M12 plus A23 into determinant of, sorry here, determinant of M13. M13. So you'll get this. So now this entire thing is like as if what you've done is you've computed a determinant of, if you repeat one of the things, it will be like you have, instead of A11, now you're writing it as A21, A22, and A23. And then minors were defined the same way. So there is no change in the remaining part of the matrix. That is same. This is A31, this is A32, sorry. Okay, this should be A32. My bad. So A32, and then you have A33. This is the matrix that you would have. Now, in this case, one of the rows is repeated. So if you would account for that, if you would substitute the repeated row in this fashion, then this formula can be shown to reduce to 0. So as you can see that I've already marked here that this term A12 into A21 into A33 is this term. So this gets cancelled out. Then this term is also getting cancelled out with this term. As you can see, A21. No, not this term. This is getting cancelled out. But there should be a mistake here again. There should be 2, 3. Yeah, no, it's okay. So this will cancel out with this one. And same way, you would have one more term cancelling out, A22, because you've placed it with A22. So this will cancel out with this one. So eventually you'll get a 0. So if you have a repeated row, what I'm trying to say is that you'll get a 0. So matrices which have uh, repeated rows can be shown to have a 0 entry in the diagonal form. If you wanted to reduce using some operations, it will have a 0 at the end. That you can also claim that, because determinant, as I said, is a product of those diagonal entries. And if the determinant is 0, that means one on the diagonal, at least one of the diagonal entries is 0. So that would mean that you sort of, and that you can readily see if you have a repeated row, you would be able to reduce one of the rows completely to 0, which means one of the diagonal entries would be going to 0. Anyway, so what are these? Another way of looking at these determinants as um, areas of the column vectors that make the matrix. So let's say if you have columns of the matrix. Let's say this was matrix A, and it's for 2-dimensional, you'll have two matrices like this, two vectors like this, which are 2 cross 1. Both of them are 2 cross 1 vectors, right? So these are two vectors. We can sort of say these two vectors are, let's say, A1 vector and A2 vector, and they're forming, now you can form a parallelogram using this. So area of this parallelogram is what is given by determinant of this matrix A. Now, if these vectors are linearly dependent, that means they can be represented in the sort of in terms of one another. Then you are saying that suppose if one of the vectors is A1, the other vector is lambda times A1 because they're linearly dependent. In this case, your parallelogram would have a 0 area, and so your determinant also goes to 0. Okay. Same way for a 3 cross 3 matrix, you will have a parallelepiped, and for that the determinant would be given by the three vectors that forms the parallelepiped. You have A1, A2, and A3. So these vectors form this, and then the determinant of that would give you the volume of this. Now, if your one of the vectors is repeated, then you will have essentially a plane and not a 3D parallelepiped, and so the volume will go to 0. That's what the determinant of 0 would indicate. So if you extend this concept to n cross n matrices, you will see that we perform the same way. You pick a row, whichever row you want. Here we have again picked the first row for calculating it. So determinant of A would be given by A11 into determinant of the submatrix, we call it M11, minus A12 into determinant of M12, which will be leaving this column and this row. You will have this matrix, these set of vectors of the submatrix forming the submatrix, which the determinant of what you will have to compute here. Correct? Now, in general, you'll have for the kth element here, you'll write this as minus 1 to the power 1 plus k. So you have plus here, minus, then again plus, then minus, then plus. It alternates. So for the kth element, well, the sign would be given by minus 1 to the power 1 plus k. And the determinant of m1k. So you will have this. Then you would get n such terms. In the short form, you can write determinant as a1k into determinant of m1k and minus 1 to the power 1 plus k. Now suppose if I want to choose, instead of the first row and first column, I want to choose, let's say, the ith row. Okay. So I can choose the column also, by the way. So instead of, for example, I could have chosen this column for my calculations. It will run from plus, minus, and the matrices that you will form would be same way. For this element, the matrix would be given by this. For this particular term, the matrix would be given by, you take away this part, and you take away this part, and this plus this part together will form the submatrix of the determinant of which you can calculate. So with the column, you can pick a row or column. Here we'll talk about only picking rows. So let's say if instead of picking the first row, if I pick the ith row, okay, if I pick the ith row, then the only thing that I have to do is replace this one with I, and the remaining things you know exactly how it will form the sum matrices and all. So if you pick the ith row, the determinant would be given by this expression, which is same as previous one, only one has been replaced by I. So you can I where I can be 1, 2, 3, so on, or n, whichever row you pick. So it depends on how you sort of want to compute. So this way, suppose if we sort of for each row, if you want to go about it this way, then you'll get these terms. Let's say uh, this term that you get here, which you're multiplying with aii. That's sort of if you collect all those terms for each row, then you can form a matrix. You can say Cij is nothing but it's a collection of all these quantities, determinants of submatrices, right? So you can form a matrix by using those as the components. Such a matrix is called the cofactor matrix. Okay. Now, suppose if you are uh, looking at the determinant, you can say that you just take one row of so what you do is essentially you will say you will multiply aij with the determinant of this particular thing. That means you're multiplying aij with cij, and the summation is going to give you determinant of a, correct? And for any I, for for any I, you can pick any I, but you have to pick the corresponding values of cij corresponding to that particular I also. Okay. So for any I from 1 to n, and that will give you determinant. The interesting thing is, suppose if you don't pick, so suppose if you want to write it as aij, and then if you take, let's say let's say if you pick a1j, but here we are picking c2j, okay, and then we are sort of running from j equal to 1 to n. If that's what we're doing, we're picking the first row of a and the second row of this cofactor matrix, then you can show that this is going to be 0, because it will be like calculating determinant of a matrix with repeated rows. Because what you would have done is, by when you're multiplying with c2j's, you would these terms that you've obtained are corresponding to a different row, and now you would have at least that different row you are substituting with a row which you have included in the calculation of these determinants of the submatrices, correct? So therefore this product will go to 0. So it's important that this is aij and this is cij. That means a1j, c2j is what? Summation over j is determinant. a2j and c2j summation over j is determinant. a1j into c2j summation is actually 0, because it corresponds to determinant of a matrix with repeated rows that you can work out back at home once more to convince yourself. We have already done that calculation here. So it's the same calculation as this one. Exactly the same thing as we had done here is what you're getting there also. So that you can convince yourself with. But with this information, if you proceed now and define some sort of something called a classical adjoint or adjugate matrix, which is nothing, will denote it by adjoint of A or adjugate of A as C transpose. Okay, so adjoint of Aij is essentially Cij transpose, and then now very soon you would realize why it is taken as a transpose. Okay, why there is a need to define adjugate in this fashion? You know, So in any case, then the Cij transpose would be minus 1 to the power. These terms would be I plus j, because it doesn't matter j plus I or I plus j. So we are using this definition here, okay, to define these terms. Only thing is we're taking transpose, so we're replacing j with I and I and j. In this case, minus 1 to the power I plus j is same as j plus I, so we'll leave it like that. But the determinant of the sum matrices has to change this way. It will be ji and not ij anymore. Okay. With this thing in mind, now if we go to the product of matrices, let's say if you want to multiply A with adjoint of A, let's see what we get. We'll get another matrix, let's say B, if you do this. Let's call this matrix B. So the ij component of B would be given by, as we had seen using the product definition for matrices, so aik into kj component of the adjoint, and the k has to run from 1 to n, right? We replaced the definition from of adjoint here, and this would be essentially minus 1 to the power k plus j into determinant of mjk. So you can see kj would be jk, like ij was ji, same way. So ij becomes ji, kj becomes jk. That's the thing. Now you can immediately see that if this is nothing but, this term is nothing but, you can write this as ik and cjk, correct? And as we had seen earlier, the determinant is given by if j is equal to I. So if I equal to j, you get aik into cik. Now aik to cik is determinant of A. Okay, that means all the elements Bii, all the diagonal elements of the matrix B are equal to determinant of A. But if I is not equal to J, then you will get aik into cjk, where j is not equal to I. And where that we had seen, it goes to 0, should go to 0, because it's the case of repeated rows, correct? So the B matrix that you get now is essentially having, is a diagonal matrix with all the diagonal entries given by determinant of A, correct? This is your B matrix that we have defined, correct? Now, determinant of A is a number sort of belonging to that field, so we can bring it down. So you get A into adjoint of A divided by determinant of A as identity matrix, correct? This means that this matrix must be A inverse, because that's giving you an identity transformation. So then you can define A inverse as adjoint of adjugate or adjoint of A. Here, when we say adjoint, we mean classical adjoint and not adjoint, okay, for a general matrix. So the classical adjoint of A divided by determinant of A gives you the A inverse, correct? Yeah. So there are certain properties of inverses that we can note here. This is coming exactly the same way you can, the way we have talked about transposes or adjoints. So if you have a mapping A to B, let's say in this case, this is you're doing first B and then you're doing A. So together you're doing something like AB, let's say. And when you want to do AB inverse, you have to first do A inverse and then do B inverse. So AB inverse would be doing like A inverse first and then multiplied by B inverse. That's what this is, the property. Same way, A transpose inverse would be equal to A inverse transpose. Determinant of A inverse is going to be 1 by determinant of A, that you can show using this property. This definition, you can show that. Inverse of an inverse is essentially getting the same transformation back. And if A is invertible and you're given an equation with A, like AB is equal to AC transformation, then you can say B is essentially A inverse AC, and that would be I into C is C. That's clear that you get the C back. And If A is invertible and you're given this kind of equation, you can say B equal to C. However, we have to keep sort of be careful here. If you're given BA is equal to AC, then you cannot say this right away, even if A is invertible. What can you say then? If A is invertible, what you can say is B is similar to C, but B is not equal to C. So this would imply B is similar to C. Why? Because you can say it is A inverse BA, and it's like a similarity transformation is equal to C, which indicates that B and C are similar, but they're not equal. Same way, if A is invertible and you're given A B equal to 0, then you can say B equal to 0. However, if A is not invertible, then AB can be 0 without either of A or B going to 0. Right? So if A is singular or non-invertible or not invertible, then AB equal to 0 does not imply A equal to 0 or B equal to 0. It does not imply that. Okay, that's an important thing to keep note of. Now we'll move to Cramer's law. I'm sure all of you must have seen this, done this in 10th standard or 12th standard, and this is one of the ways that we were shown to find solutions to small matrix systems like 3 cross 3 or 4 cross 4, and that's how we used to solve them. The idea was that you have to solve for you're solving Ax equal to B system. So from there you can say X is going to be A inverse B, correct? Now, if X is A inverse B, and we have now found another way of writing A inverse, which is adjoint of A into B, correct? That's another way we have found. Of course, adjoint divided by determinant of A. That's the way to do it. Now, using this definition, suppose if you want to write the solution component, jth component, let's say here, as we are doing here, xj component. So I should write it as the jth component of x solution, solution x would be adjoint of jk into bk summation k equal to 1 to n. It's like operating a matrix on a vector. So that is the determinant of A is common factor. It's a number, so you can bring it out. So you can say this is BK into, as we had seen, adjugate of A is essentially transpose of CJK. So you can write this as CJK transpose. CJK transpose is nothing but CKJ. So you can write this as BK into CKJ. Now, suppose if I replace the kth column of the matrix A with BK vector, then I can what I'm doing is then I'm saying A, let's say A JK. Let me write this as AKJ as BK. Okay, that's what I'm doing. So if I replace that, then essentially what I've done here is, while calculating the determinant, if I just change these values B1, B2, and so on, and I'm instead of rows, I'm using columns now. So if I use this column to compute the determinant, then I'll say B1 into the determinant of the remaining submatrix, which is going to be represented by the element C1J. Same way, I can remove this column in this row, and then the submatrix that you will get from the remaining terms, you'll get that thing. So that essentially is what going to give you a determinant of a matrix with the jth column replaced by the bth, by column B, correct? So essentially you'll get this summation bk ckj would be nothing but determinant of the jth column being replaced by B. And therefore you get you say that my solution, the component jth component is given by determinant of bj divided by determinant of A, where bj is this matrix obtained by replacing the jth column of A by the right hand side vector B, correct? This part you know already, right? Right. So finally, now we'll take note of some properties of determinants before closing this class. So let's look at them. Determinant of I, identity matrix is always 1. And you can just say 1 into 1 minus 0 into 0 gives you 1. Correct? That's how you will do it. Determinant of a product of matrices is given by determinant of A into determinant of B. Okay? Just like trace of AB is trace of BA. But a trace of AB, you can note that trace of AB is not equal to trace of A into trace of B. That is not true. Okay, that you can show. That's not true. But here, determinant case, determinant of AB is determinant of B. A into A, determinant of A into determinant of B. On the other hand, we can say trace of A plus B would be equal to trace of A plus trace of B. That's an obvious equation that you can write. But here, as you will see, determinant of A plus B is going to be not equal to determinant of A plus determinant of B. That is not true, right? So because determinant is found by product of these values, so so the products of lambda 1, lambda 2 to lambda n multiplied by lambda 1 prime into lambda 1 prime is same as the product that you will get from here. That's the, you can think of roughly that. Trace is formed by addition of eigenvalues, diagonal values of the once you have performed the similarity transformation. So their addition is the operation that you will sort of worry about. Okay, so that's the way it goes. So you just keep note of this. Trace of A plus B is trace of A plus trace of B. Determinant of A plus B is not equal to determinant of A plus determinant of B. All right, so when you change the rows, you would see that you would have to change the sign. So changing rows, you can think of it as a process of doing a permutation of rows. So let's say if you had this matrix, same thing that you have here. If I use, let's say I'm doing an operation on A11, A12, A21, A22, and I want to change the rows, I say I will write this. Now, if you do this, then you'll get 0 in 0 into A11, 1 into A21, and you add them, you get A21. Similarly, you get A22. Here you get A11, and here you get A12. And using the property, determinant of this matrix into determinant of this matrix would be determinant of this matrix. Correct? So determinant of this matrix is nothing but 0 into 0 and minus 1 into 1. So it's minus 1 into determinant of A11, A12, A21, A22 is equal to determinant of the row exchanged matrix. This is A11 and A12. Correct? So you get the minus 1. So determinant of a permutation matrix is therefore minus 1 always. So in this case, it's a 2 cross 2 matrix, but in some cases, you would have n cross n matrices where you will be doing permutations like this, row exchange, especially used for pivoting or some operations like that in numerical linear algebra. There, I think you will have to keep a note of this. Anyway, so you have now, if you can exchange, instead of just rows, you can exchange columns also. So when you exchange columns, then again, you introduce a minus sign. Same way. But if you do 2 exchanges, then one exchange is minus 1. The other exchange will also be minus 1. Then 2 exchanges, 2 permutations will make it 1. So determinant will come back to same thing if you exchange twice. Now you can decompose the determinant into 2 pieces also. You have A11, A1 prime, and you can split it into 2 pieces like this, right? So determinant of such a matrix where one of the rows is split into 2 pieces, it will be same as determinant of one matrix and the splitted, 2 matrices with the splitted rows like this. But as we had discussed earlier, this does not mean that determinant of A plus B is determinant of A plus determinant of B. Here, this is just one row being splitted, not the entire matrix. Okay, so that you have to keep a note of. Now, using this property, we can say, suppose if you split it in such a fashion that you are having beta times A11 into beta times. So you are replacing like 1 times, 2 times, and beta times. So you'll have beta such terms coming here. So same set of terms coming beta times. So you'll get beta times A11 into beta times A12 is beta times the determinant of this. So it's like scaling. So if I choose beta to be 0, so that means one of the rows goes to 0, then you can clearly say that my determinant also goes to 0. Correct? Now, same way, column. Same things can be said about whatever can be said about column rows will be said about columns also. But what if you scale all the elements? That means you're writing beta times A and you're looking at determinant of beta times A. That means you're scaling all the elements of A by beta. You can think of it like you had the vector A1 and A2 and you increase this by 2 times, let's say 2 times A1, and this you increased by 2 times A2. Then the area of this new parallelogram is going to be 2 square times, right? It's going to be 4 times. So same way for an n-dimensional space, you'll say it will be beta n times. This hyperspace volume of determinant of dA, beta A would be beta n time, beta to the power n times the volume of the hyperspace created by the vectors, column vectors of the A matrix. Same thing. So this is another property. Now, if you have repeated rows and columns, as we had seen earlier, that they reduce the determinant to 0. It can be shown that determinant of A would be same as determinant of A transpose. Which means that if A is singular, then the transpose or the adjoint of that matrix would also be singular. Okay. If you have triangular matrices, then the determinant is given by the product of the diagonal matrices. That gives you the determinant. If it's a triangular matrix, of course, you have to sort of see that it should form all the lower diagonal terms in the matrix below the diagonal are all 0. Or similarly, above the diagonal all are 0. In these cases, the determinant is given by the product of the diagonal entries. Trace also this will remain invariant, of course, then A11 plus A1, A22. Anyway, that doesn't change, but product will sort of given by this. Okay. Now we are done with the determinant part. We'll just the next class we'll talk about spectral decomposition, and that's where we start talking about definition of eigenvalues and eigenvectors. So we'll close this class here.